Hey gang, welcome back. Just wanted to let you know we're finishing up our semester review, part 3. Please watch all 3 videos and then send me an email. Make sure I got all your information. Great. So we're going to be talking about redox, reduction oxidation reactions, how do we make batteries, and hydrocarbons. So on the point of redox, the most important thing of redox reaction is oxidation, oxygen. It's all about oxygen. Are there times when oxidation doesn't involve oxygen? Well, yes. It's really an exchange of electrons. But we have this huge word here, 17 letters, electronegativity. Oxygen is the most electronegative element on the periodic table. It is most likely to exchange those electrons, to pass them off. As we're looking at its picture, its orbital diagram, we have our oxygen in the middle here. It's got its S shell. It has its P shells. But this third P shell, because we always have to have 3 P's, 3 P shells. This third shell is empty. It makes the atom kind of wobble back and forth, side to side, and it's unbalanced. Going back to that balance thing again, everything needs to be balanced. So it goes looking, it goes searching for other electrons to fill that third P shell up. Oftentimes it finds hydrogens, because hydrogens are very bonding as well. They're very common. So it joins in with those oxygen and it balances that third P shell out. Now at the same time, this hydrogen only has half of a wheel. Driving down the road with half of a wheel doesn't work very well. So it's desperate to find another electron as well. So this oxygen and these 2 hydrogens get together, they bond, they have a covalent bond that allows them to share these electrons, and they make a water molecule. Okay? These redox reactions are reversible. They can go back and forth. As we looked last time, we're talking about rust again, and rust is an oxidation reaction. So anytime you're adding oxygen to the base reactant, this iron has no oxygen in it, and then all of a sudden you add some in, and it turns into rust, iron oxide. But this reversible reaction, you can put some fire in it, split it back apart, turn this rust into iron. Iron that we use in all kinds of technologies. So as we're adding oxygen, we have an oxidation reaction. It turns it into rust. It's an exothermic reaction, which also means it's a spontaneous reaction. If you drop a chunk of iron in a puddle of water, it doesn't need any extra help to become rust. It's going to do it all by itself. It's spontaneous. However, this reduction reaction, where we're pulling that oxygen out, that's an endothermic reaction. You have to add a little bit of heat to that. You got to put some fire to that iron ore to get it to clean up and be iron. We know how likely these different oxidation and reduction reactions are going to occur by what we call the oxidation number. When we say the oxidation number, we're talking about the number of electrons that atom has to share. When it forms a molecule, you get these 2 atoms coming together and they're sharing these electrons. Well, this oxidation number tells you how many of them electrons are out there ready to be shared. Oxygen on primary is always a -2. 2 holes for more electrons. I need more electrons. It's missing 2. My hydrogen says, hey, I've got a spare electron. You can have it. We'll share it. We'll bond ourselves together and we'll make everything balanced. One application of all of these redox reactions that we live in, batteries. How do we power our society? How do we power our cities? Can't always be plugged in. Can't always have a generator sitting, spinning that magnet around. So we've got batteries. Well, about 1800, Alessandro Volta, where we get the volt, the voltaic battery, he lined up a block of ions that have a negative charge. An anion, if you remember back a long time ago, an anion is a negatively charged ion particle. So an anode is a negatively charged battery cell. Similarly, our cation was a positively charged ion particle. Cathode is a positively charged battery cell. So we put an electrode between them, and these electrons, as they're sitting over here with all this potential, all this desire to move out and find balance, they go across this cord, this electrode, and move the electrons from here to here until all of them are balanced out, and it's a nice even flow. We make use of these batteries. I had my daughter tell me it doesn't look like a AA battery. So it's a D. Okay, so I've got half of my battery that's got a negative charge in it. And there's an insulator between the two that keeps those electrons from flowing. And then on the top, I've got positive charges. These guys are desperate to find that balance. I can't go through the insulator, so I'm going to find whatever route I can find. They're going to go along this wire, light our light bulb, because they got to go through that, and then they come all the way back down here to where the positive side are so they can find their balance. Now remember, we've only got 4 electrons on there, but really there's trillions. These things are submicroscopic. We can't see them, we can't count them. Trillions of these electrons are flowing across this wire to make this electricity happen. Another use of a battery is an electrolytic battery. We have an electrolyte solution inside the battery that serves to keep those electrons separated. So my oxidation reaction is when those electrons are coming out, going out to start the engine. Start it up. Once that engine's running, I don't need to do that anymore. I don't need any more electrons coming out of the battery. So I use my alternator and cause a reduction reaction by forcing more electrons in, charging that battery back up again. Another use of redox reactions is electroplating. It's an oxidation reaction. I'm taking this silver and I have electrons waiting, waiting on the edge of this surface of my jewelry, this other metal. Got this electron saying, gimme, 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 I need my balance. So these silver ions, positively charged ions, cations, bond with the electrons that are sitting on the surface, and we have silver-plated jewelry. And finally, we're going to talk about hydrocarbons. Get us caught up to where we're up to, and next week we can start some new material. So as I'm looking at my carbon's always got those 4 different bonds. It's around the outside, looks very orderly, set up. It's very common, easily bonded together. So it's always going to sit and try and make all these bonds. We call it organic chemistry because everything that you burn for fuel, coal, gasoline, they're all based on a hydrocarbon chain. Everything that you eat for food, it's all based on a hydrocarbon chain, whether it's meat or vegetables, sugars, they're all based on these hydrocarbons that allow things to burn. Different ways that we can organize these hydrocarbon chains. Single bonds, all bonds in this particular chain are single. We call those an alkane. If there's a double bond, they don't all have to be double. They just have to have at least one double bond. We call those alkene. And if there's a triple bond, again, not all of them, just one, if it's an alkyne. So as we're talking about saturated foods, saturated fat, these are the alkanes. These are those foods that we eat. There's no more hydrogens that can go in there. They're saturated together. In here, he's got this extra bond. It takes a little bit of extra energy to break that second or third bond. They're unsaturated. You can put more on. So the healthiest food we can eat would be an alkyne fat. Alkyne unsaturated fat. Of course, nobody shows that on their label, so you just got to go with unsaturated. As we have branches coming off the side of these hydrocarbon chains, those are alkyls. Notice how all the words kind of sound the same. Alkane, alkene, alkyne, alkyl. That's how you know it's a hydrocarbon chain. All of these different groups coming off of the side here have different functions. The next lesson we'll get into what we call functional groups that break down and tell us the way these different atoms are going to behave, some of the purposes they might fulfill. This particular one is an amino, as in an amino acid. Builds into proteins. All these different alkyls cover down on the hydrocarbon chains and cause different things to occur. One specific case would be a hydrocarbon ring. Very common. They like to bond with themselves. Because they can bond so easily, they bond with themselves as well. We know it's a benzene ring because we have a double bond and it's got ene, just like an alkene. Okay? Great, that brings us up to date. And just so you know, it's not that easy to put 10 chapters of review into 1 week. So I hope you enjoyed it, and I hope you got a lot out of it, and I'll see you again next week. Check in on the teacher page.